All right, so 1.3, example 3. We're looking at the end behavior again, and we have 3 different examples here, and they're all kind of similar but slightly different, and you'll see how. So it says to evaluate the end behavior of the following rational functions, and as always, it should go without saying, but I'm still saying it here in the beginning, use correct notation. All right, so if we're looking at the end behavior, we're finding the limits, right? The one-sided limits as x goes to what? Infinity. And again, once you put the limit there, make sure there's something behind it. You have 2 options here. You can either put the entire expression, because that's what we're going to be evaluating, or in this case, because it has a name f of x, we'll probably choose just to do that. Mrs. Lincoln, everyone. You remember her? All right. Okay, so you can put f of x. That's the what end behavior, left or right? Right end behavior, good. And then as x goes to negative infinity, it's a left end behavior. So when you have a quotient of 2 functions, it's kind of interesting. You can analyze how fast the numerator and the denominator grow with respect to each other. And there's only a couple of things that can happen. Either the bottom is going to grow faster than the top for large values of x, in which case what happens to your ratio values? It gets smaller, approaching 0. It could be the top gets bigger faster than the denominator, in which case your ratios will get really, really big, either in the positive or negative direction, magnitude-wise. Or it could be that they're kind of growing at the same rate and they kind of divide out. So just like with the polynomials, because we're looking at end behavior, you can just analyze the leading term in the top and the bottom, which, remember, are not always in the front, but in this case, they are, because they have the largest exponent. So if we look at that right there, the 3 and the 5 really don't have any bearing as a primary investigational tool, but the exponents do, and possibly the coefficients later on. So you look at the exponents first, x squared over x cubed, and of course for huge values of x, which one grows faster? The bottom, right? And we're going out to infinity, so we have forever and ever and ever to do that. Eventually the bottom is going to get so much bigger than the top that the ratios will get closer and closer and closer to 0. Yeah. Now the difference here is only 1 degree. It's x squared over x cubed. It will still go to 0. If it were x squared over x to the 4th, and the difference was now 2, it would go to 0 a little bit faster. If it were x squared over x to the 5th, it would go to 0 a little bit faster. But is it a race? No, because we have for how long to get there? Forever, yeah. So what's going to happen as you go out to the left? Should it be the same thing? No? You do have a negative, but it won't be approaching 0? No, it'll actually still be approaching 0. Now let's look at what the negative does to it. 0 is the x-axis, right? Y equals 0. So anything above the x-axis is positive, and anything below the x-axis is negative. So this is kind of interesting, but you can determine if it's approaching the x-axis from above or below. Let's see how we can figure that out. Plugging in a positive representative to go out to the right end behavior, 3 positive squared over 5 positive cubed is positive. So all your y values as you go out to the right are going to be positive and approaching 0. So it should be approaching the x-axis from where? Above or below? From above, right. Now that's really just extra information. If you're trying to sketch it, that might be helpful. And for negative infinity, if you plug in a negative representative, 3 negative squared is positive, but 5 negative cubed is negative. So positive over negative is negative. So as you go to the left, all of your y values are negative, but still approaching 0, so it's approaching the x-axis from below. Yeah. Now, locally, we don't know what's going on, but here's kind of what the graph's doing. As you go to the right, it's approaching from above. As you go to the left, it's approaching from below. And then in the local behavior, it could be doing any of this crazy stuff. We're not sure. We're just looking at the general trends to the left and right. So there you go. It doesn't matter if it's positive or negative. If the bottom grows faster by any amount, it's always going to go to 0. Which means from yesterday, we could say what graphical feature lives there? There's a horizontal asymptote at y equals 0. Make sure you say y equals. Because the vertical is what? X equals, yeah, and the horizontal line is y equals. Okay, so that you can think of that as case 1. Anytime the bottom grows faster than the top, it's always going to approach 0. All right, part G, let's put in some missing negative signs. Looks like there's 3 missing. Very similar looking function, but now if you analyze the degree of the top and bottom, the top is degree 5 and the bottom is degree 5. So everything else behind the leading terms will totally affect the graph locally in the short term, but in the long term, they become increasingly insignificant. So you look at the leading terms again. So this function will be approaching this ratio, right? The ratio of 3x to the 5th over 5x to the 5th. Of course, infinity to the 5th over infinity to the 5th, when it's the exact same infinity, what's going to happen with those two values? Yeah, they increase at the same rate, so they should divide out, and we're left with what? 3/5. So that should be the end behavior. The limit as x goes to infinity of g of x now should be 3/5. And it's a little bit harder to tell if it approaches 3/5 from above or below because we're not just looking at signs, positive or negative. So we're not going to figure that out today. The limit as x plus u goes to negative infinity should be what? Is it also 3/5 or is it negative 3/5? Should be the same. Yeah. Now notice why it's the same. And this is important for what we're going to be doing here in a little bit. These are odd degrees, so they will preserve whatever sign of x you plug in. You plug in a positive x, it's going to stay positive. If you plug in a negative x, it's going to stay negative. But they're both positive 3/5 because positive over positive is positive, and negative over negative is still positive. So when the degrees are the same or they're growing at the same rate, it's always going to be approaching the quotient of your leading coefficients. Okay, and it's not going to be plus or minus. It'll always be the exact same number. That's in the long run. Of course, in the short run, all this other stuff will affect it. So there will be a horizontal asymptote at y equals 3/5. And whether it approaches from above or below, if we were interested, we would probably be sketching it, and we'd collect other pieces of information that would help us figure that out. All right, so the first two cases, we do have horizontal asymptotes, right? The first one, the bottom grows faster. By any amount, it's always, always, always the same number. It's always what? 0. When they're growing at effectively the same rate, x to the 5th, x to the 5th, x to the 20th, x to the 20th, whatever, then it's always going to be a horizontal asymptote, but it'll vary, right? It'll always be whatever the quotient of the leading coefficients are. So in both of these examples, we have two end behavior asymptotes that are horizontal. So what would be the third case? Right. We have the bottom growing faster, growing at the same rate. I guess the next one would be top grows faster. So we'll call this dude h of x. No missing negatives. What do you know? Interesting how it picks up some but not the others. All right, so the leading term in the numerator is 4x cubed, happens to be in the front. And in the denominator, it's negative 2x squared, happens to be in the front. So for the end behavior analysis, we'll go ahead and write the limit as x goes to infinity of what? What goes next? H of x. Good. Don't leave that off. And the limit as x goes to negative infinity of h of x. So again, look at the degrees before you look at the coefficients. X cubed over x squared. For large x, x cubed grows faster. And so the magnitude, I should say, of the ratios are increasing, right? They're both getting bigger. If you plugged in right now, this is really infinity over infinity. And while I'm here, let me just mention that. Infinity over infinity is what we call an indeterminate form, as is 0 over 0. Okay, let me write that out. These are indeterminate forms. And why are they indeterminate forms? Because when you plug in and get 0 over 0 when you're evaluating the limit, you cannot determine it by direct substitution. It doesn't necessarily mean undefined, but it still could be. We saw in our warm-up that 0 over 0 meant what? 4/3? 0 over 0 could mean 4/3. It could mean 7. It could be whatever the y value of the whole is. You just have to do a little bit more work. What is the reciprocal of 0? Did we talk about that? Yes. The reciprocal of 0 is what? Infinity. So really the reciprocal of 0 over 0 is infinity over infinity. These are reciprocals of each other. So it's just kind of the other side of the coin. This is also an indeterminate form. Infinity over infinity doesn't equal 1. It could equal 1, but it could equal something else. Both of these cases over here were infinity over infinity, weren't they? If you plug in infinity for x, you get 3 infinity squared over 5 infinity cubed. That's infinity over infinity. But what did it equal? 0. Over here, this was infinity over infinity. But what did it equal? 3/5. And over here, we also get infinity over infinity, which is an indeterminate form. We have to come up with some other way to figure out what it is. Now, in this case, because the top grows faster than the bottom, we know for huge x, it's going to get infinitely large. So you know it's going to be some type of infinity. So I'm going to throw infinity down on both of them. For step 2, then, we come back and we need to figure out which infinity it's going to. There's only 2 types, right? Since we're talking about y values, it could either go up forever or down forever. And a 50% chance of guessing correctly are pretty good odds, right? So I like those odds. But I'd like to get better odds. So how are we going to determine which one? Plug in, right? We've done that a lot with vertical asymptotes. We plugged into the left and right. You can always plug in values, right? Remember in Algebra 1 when you're trying to figure out what graphs look like? You made a little table of values over here. You chose some x values independently, and then you plugged them in and got y values, and you plotted them and made dots, and then you connected them. You could always plug in ordered pairs to figure out what's going on to help yourself. So if we're going to positive infinity into the leading terms only, what sign do you get when you plug in a positive number for x? In the top, you get 4 positive cubed, which is positive. And on the bottom, you get -2 positive squared, which is negative. So positive divided by negative is negative. So, there you go, negative. And as you go up to the left, if you plug in a negative representative value, 4 negative cubed is what? Negative. And -2 times negative squared is, well, negative squared is positive, right? -2 makes it negative again. So we have negative over negative, which is positive. So those are the answers. Now, of course, on a free response, you could also say what? DNE, right? DNE, the catch-all answer. Okay, so there you go. You can always figure it out. It doesn't matter if the degree difference is, in this case, 1 cubed over squared. It could be x to the 4th over x squared, a degree difference of 2. It's just going to go to infinity or negative infinity faster. But again, it's not a race. So that's one way you can determine what the limits are. Oh, by the way, is there a horizontal asymptote here on part C? No, because neither one of those are a finite y value. They're both infinite. Okay, there's another way that we can determine what the end behavior is. Not that that was very difficult, but every time you have a rational expression, you can look at what's called the end behavior model. And the end behavior model is basically what you would see on a graph if you were to zoom out and keep zooming out. Okay, like if you're looking at it up close, imagine you're hovering over like a street, and then you start going up into outer space. That'd be cool. What do you see from afar? You're not going to see the local behavior. Every function is going to begin to look like its end behavior model. And here's how you could figure out what the end behavior model is. Let's come back over here. We analyze the leading terms, right? What would you get if you just simplified the leading terms? I'm going to put end behavior model, EBM. It's going to be y equals, and just simplify the leading terms. 3x squared over 5x to the third simplifies to what? 3 over 5x. Good. That is your end behavior model. Of course, that's the same as 3/5 times your parent function 1 over x, right? And what does that look like, your end behavior model? Well, 1 over x is your reciprocal function, right? It lives here in quadrant 1 and in quadrant 3. And the 3/5 is just going to make it a little bit shorter. It doesn't reflect it or anything. So it still kind of lives in here and here. That's your end behavior model. which means this function right here on part A, if you were to zoom out into outer space, you would not see any vertical asymptotes or local max or mins. It would just look more and more and more like this. Now, why do we call it an end behavior model? Well, the end behavior model and the function itself will have the exact same end behavior. So let's see what 3/5 1 over x does. As we go out to infinity, what does it approach? It approaches 0 from where? Above, right? Is that what we came up with? Yep. And as we go out to the left, 1 over x approaches 0 from below. So that's another way to do it. You can figure out the end behavior model and look at its end behavior. All right, let's look at this one over here. Part B. The end behavior model, the EBM. Just set it equal to y because it'll be a graph. Simplify these, and what do you get? 3/5. Okay, now what would the graph of 3/5 look like? What kind of straight line? A horizontal straight line, yeah? So whatever this function looks like, it's probably got some really interesting local behavior, but as you zoom out more and more and more, you're just going to see a horizontal line at y equals 3/5. So what would be the limit as you go out to the left and right on the horizontal line 3/5? 3/5, right? You're on the same thing. So again, your end behavior model is what you would see if you zoomed out, basically looking at it from outer space, and it would have the same end behavior. Now let's look at this one over here, because this one starts getting interesting, because we had horizontal asymptotes there on both of them. This one, your end behavior model, is going to be y equals what? Simplify the leading terms. Negative 2x, right? Which would graph as a what? Another straight line, but not a horizontal line, a diagonal, a slanted line. Now, a line is going to be of the form mx plus b, so there might be a y-intercept there. I'm just going to say plus b for now, which we don't really need to know where it is vertically. But if you were to sketch a line, negative 2x, it would look like this, right? It would have a slope of negative 2. And so notice that because the line, as you go out to the right, goes down, so should the original function, right? As you go out to positive infinity, it goes down to negative infinity. And on the line itself, if you go out to the left, the line goes up to positive infinity. So it's another way to determine the end behavior. Now let's do something here. I want to actually sketch on the calculator, and you can just kind of watch along. I'm going to go ahead and type in the entire function on part C, h of x. And I'll zoom in closely, and we could talk about the extreme local behavior, right? You could see local maxes, local mins, x-intercepts, y-intercepts, drunk people on the river. That's different local behavior. And then we'll zoom out, and then we'll lose all the local behavior, and we'll just see what appears to be that line, okay? Should be kind of fun. Let me load my calculator here. If you want to play along, feel free. If not, just look on. I think I'll go to the big screen here. You'll feel like you're in the IMAX theater. Not really. No school on Monday. Did y'all hear about that? Yeah, I heard about that too. Have to admit, I'm kind of disappointed. Some people still practice, like volleyball still going to practice. Is band still going to practice? No? There you go. All right, so let me type it in. There you go. I typed it in, and I'm using the new math print. Every time I demonstrate something, I'm using the new math print, which is nice because you have the horizontal division bar, which you don't need parentheses. So if you have your own calculator and it's an 84 and you don't have math print, I can infect you with that new operating system. Just bring it to me sometime. Okay, so there it is. And look what I graphed in y sub 2. Actually, I'm going to get rid of that. I don't know where that came from. Okay, let's graph that. Zoom 6 is a good place to start if you're not sure what the graph looks like. That's your standard negative 10 to 10 viewing window. All right? Ooh, right? Look at that. Look at this local behavior. Ooh, see it right there? It's kind of like, whoa, it's kind of wiggly, That is so awesome and interesting, isn't it? Okay. Let's zoom out. Okay. Now, a way you could zoom out on your calculator is just hit the zoom out, right? Number 3. And what it does is it puts the cursor at the origin, which would be your center of the zoom, and it zooms out equally on the X and Y axis by the same scale. So hit enter, and it's like we're floating up. Now you just see the railroad tracks. Let's do this. Let's turn the scales off. If you go to Window, X scale to 0, Y scale to 0, that means you won't have tick marks, so you won't get fat axis. You hit graph there. You can still see the local behavior, can't you? It's right here, but you don't get like the detail. But it is starting to kind of look like a line, isn't it? Let's do it again. Zoom out, zoom 3, and again I'm at the origin there. And did you see the local behavior right there? I mean, just a smidgen of a wiggle, just a smidgen, but it was still there. Now you don't have to hit zoom out again if you're still in zoom mode. Just hit enter. Look for the local behavior. I didn't see any. Let's do it again. Zoom again. Nope. Do it again. We are like in another solar system now. That's how far out we've zoomed. That sure looks a whole heck of a lot like a what? A line. And just guess what the slope of that line is. Negative 2x. Yeah. So again, that's what we call it the end behavior model. If you zoomed out on a function, that is what you would see. Okay, so there's a way to find the equation of the horizontal asymptote, right? When the bottom goes faster, it's always y equals what? 0. When the degrees are the same, it's always y equals what? Yeah, the quotient of the leading coefficients. Good. And whenever the degree is bigger by 1, we know it's going to go to some type of infinity. We know our end behavior model is going to be linear, which means it's going to graph as a slanted line. You are responsible for finding the full-fledged equation of what we're going to be calling a slant asymptote. Now, you can get the first term very, very easily doing exactly what we just did. Okay? How in the heck are you going to find the y-intercept, do you reckon? Plug it into your calculator and ask. Let's see. If I go back to my calculator, I'd be like, calculator, what's the y-intercept? No, not of the function. No, not of the function. Of the slant asymptote. Yeah. No, not the function. No, the slant asymptote. It's insisting on giving me the y-intercept of the function. It said to hit trace 0, which is 7/9. But that's the y-intercept of the function, not the slant asymptote, right? Remember, locally, it kind of did the whoa right there on the y-axis. It's 7/9. So let's ask again. Maybe nicer. Calculator, please, pretty please. Can you give me the y-intercept of the slant asymptote? Not going to work. So what else can we do? It was a good try. Calculator's not like Siri. Looks dangerous. That's all I need.
That's all you need.
That's all I need. The y-intercept of the slant asymptote. What is it?
7/9.
No, 7/9 is the y-intercept of the...
No, it's 0, the regular one. But
Is it 0? Well, let's see. Let's go back to Zoom 6. Here's the original function kind of... Look, 7/9 is right there. That's the y-intercept of the function. You think that the slant asymptote is negative 2x plus 0? You think it passes through the origin? Let's see. We'll see. Go to y equals, and let's sketch negative 2x plus the y-intercept you said is 0. And if it is correct, it should look like it's kissing the graph on the edges, right? Not locally, but in the end. Come on, kissy, kissy. Oh, man. Does that look right? If I were to zoom out, I do not think the blue line would start morphing into the red line. In fact, it looks like the y-intercept, if I could move The red line up or down, I would have to move it where in order to get it to be the slant asymptote? Down a little bit. So guess and check could work. We could say down 1, right? Down 1, which is what you say to a dog whose name is 1 if he jumps on your guess. Down 1. But guess and check, you might be able to get it in the region, but it's not going to necessarily give you the exact, right? So we need a better way. We need a better way. Any ideas? What? Graph only the what? The top part, just the cubic? Well, if I just graph 4x cubed over negative 2x squared, guess what it's going to give me? It's going to give me negative 2x plus 0. But how did I come up with negative 2x? I simplified the leading terms, right? Which is really 4x cubed, what? Negative 2x squared. Divided by. That's what this bar implies, right? Division. So that is exactly what we're going to do to find the equation of the slant asymptote. Okay? Here we go. Example 4. Same exact equation. This says to find, or same function, find the equation of the slant asymptote. Now, looking at it, how do you know that there will be a slant asymptote? The top is larger than the bottom by 1, okay? If the top was larger than the bottom by 2, you would have a quadratic asymptote. If it's bigger by 3, you would have a cubic asymptote. But we're not going to be finding the equations of those. So here we go, long division. The numerator becomes the what on the inside of the house? You remember? Dividend, the dividend, right? The numerator becomes the dividend, and the denominator becomes the divisor. Okay, long division of polynomials. Probably haven't done it since Algebra 2. You write it in descending order. If you've never done it, I'll teach you, okay? Here's what you do. You just look at the first terms first, and you ask yourself, how many times does negative 2x squared go into positive 4x cubed? And if you can't answer that question forthright, you come off to the side, and what you're really doing is 4x cubed divided by negative 2x squared, which we've already done, and we know to be what? Negative 2x. So that goes right there above the 4x cubed. That's how we start it. Now, how do we get the other terms in the divisor involved? Well, now we are going to distribute the number on top to every term in the divisor, and we're going to write them underneath the dividend in the proper location. So here we go. Negative 2x times negative 2x squared is positive 4x cubed. Now, at this point, those two terms should be identical. If they are not, go back and redo step 1, but this time do it more correctly. They should be correct, the same, all right? Negative 2x times positive 5x now is negative 10x squared, so I'll write it under the squared term. And then negative 2x times negative 9 is positive 18x. Okay, you remember what the next step was in regular division? You subtract. Now, when you're subtracting polynomials, it's just a little bit easier, I think, to go through and change all the signs and then add. So that'll be a negative, that becomes a positive, and that becomes a negative. We're subtracting top minus bottom. So 4x cubed now plus negative 4x cubed is 0. That should be a 0. And now we get negative 2x squared plus 10x squared is 8x squared. And then we get 4 minus 18 is negative 14x. And now you could bring down the negative 7. That was a lot of fun. I feel like doing it again. Good thing we get to. Here we go. Negative 2x squared into positive 8x squared. Well, again, off to the side if you're not sure. It's 8x squared divided by negative 2x squared, and we can get what? Negative 4. Good. So negative 4 goes up here. And We multiply one more time. We get positive 8x squared. We're going to get a negative 20x, and we're going to get a positive 36. If we change all the signs now, because we're going to subtract, negative, positive, negative, we get a 0, and then we get a 6x, and then here we get a minus 43. Now, one last consideration. Does negative 2x squared go into 6x to the first? No. It can go into something that's the same degree or larger, but not smaller. So we're done. Now let's review long division. Let's say that we had 37 divided by 5. Okay, 37 fifths. Like here we have a ratio. If you did 37 divided by 5, it would go into 37, 7 times? You multiply, you get 35. You subtract, you get 2. Does 5 go into 2? No, so you'd stop. Later on, you added zeros and decimals. But here's what we could do. We could say that 2 then is the remainder, yes? And you can write 37 fifths now as the quotient, which is 7, plus any remainder 2 left out of the original divisor or denominator 5. So 7 plus 2 fifths. Or later on, you even got rid of the plus sign, right? And you wrote them really close together, and you had yourself a mixed number. Remember that? 7 and 2 fifths. And to convert it back, you go 7 times 5 plus 2 is 37 over 5. Same thing. So the original quotient is the original expression is the quotient plus the remainder over the divisor. We could do the same thing with polynomials. So here's another version of h of x. H of x could be the quotient, negative 2x minus 4, plus the remainder, which is 6x minus 43, all over the original divisor of negative 2x squared plus 5x minus 9. Now this version of h of x could be useful for determining the end behavior and the full-fledged end behavior model. Here's why. If you take the limit as x goes to infinity of h of x, just look at this last term. As x goes to infinity or negative infinity. This is kind of like what we did up above on example A. As x goes to infinity or negative infinity, what happens to this last purple nurple term? It goes to 0 because it's x to the first over x squared. Okay, so what's the consequence of that? For huge, huge values of x, positive or negative, h of x, since this goes to 0, begins to look more and more and more like what? Negative 2x minus 4. Okay? You can almost say then that the graph of h of x will start morphing into the graph of the slanted line, negative 2x minus 4. Now, will it ever become the line? No, because this right here is actually never equal to 0, so it approaches this line. So guess what the full-fledged equation on the slant asymptote is? Yeah, so I'm going to call SA the slant asymptote. We have an SA at y equals negative 2x minus 4. Now let's see if we have to do the full long division every time. If it just asks for the equation of the slant asymptote, as soon as you get this minus 4 up here in the quotient, you do not have to distribute the negative 4 down here and get this line right here. In other words, you don't have to finish it out. Because as soon as you get the minus 4, if you're only after the equation of the slant asymptote, you have it. Okay? So how do you find the equation of the slant asymptote? You do long division, and you go through 2 iterations. Once you find the second number, you find the y-intercept, set that equal to y, and you have it. Now that's going to be useful for graphing purposes, because later on, if we know it's negative 2x minus 4, we'll come down here to negative 4, and we'll have a slope of negative 2. And you might have a vertical asymptote over here, let's say at negative 1. And if we're trying to sketch the graph then, we know that to the left of the vertical asymptote, the graph might look like that. And to the right of the vertical asymptote, maybe it lives right here. So what's neat about the slant asymptote, the y values do increase and decrease without bound. But the slant asymptote tells you not just where they're going, but it also tells you how it's going, how it's going to infinity. It's going to infinity along the stairway to heaven that is negative 2x minus 4. And as you go out to the right, it is going down to negative infinity along the AC/DC, anyone? Along the highway to hell, right? So you know not only where it's going, but you know how it's getting there. Yes, sir?
It can't touch the slant asymptote, correct?
This one probably does not, but can a function cross its horizontal asymptote? Yes, and a horizontal asymptote is an end behavior asymptote. So can a function cross its slant asymptote, do you think? Yes, okay. No end behavior asymptote is a discontinuity. So some functions do, but not every one of them does, okay? The vertical asymptote is the only one that's a discontinuity. So you're responsible for the full equation for slants. Now let's look at one other little scenario here, and you don't have to write this down, but what if you had like 3x to the 5th plus who cares, all over 2x cubed plus who cares? Of course, the limit as x goes to infinity is going to be what? Infinity. And the limit as x goes to negative infinity will be what? It'll be negative infinity? It'll still be positive, because look what happens. Negative to the 5th over negative cubed. Negative over negative is positive. So this one has positive infinity for both end behaviors. You could figure that out pretty easily. What would be the end behavior model? The leading term, at least. Simplify that. What do you get? 3/2 x squared. And there will be other pieces there, like an x term and a y and a constant. But 3/2 x squared is just a parabola that opens what? It opens up. So that's your end behavior model. If you wanted to sketch a parabola that opens up, maybe it looks something like that. Maybe you have a vertical, maybe you have a vertical asymptote here and a vertical asymptote here. So what that means is locally, the function might be doing this. Ooh, yeah, that looks fun. But as you go out to the right, maybe it's doing this. And it's going up to infinity now along the path of a parabola. And maybe it's doing this on the right-hand side. So every single rational function, if the top gets bigger faster than the bottom, you can do the long division and find the equation of your polynomial end behavior asymptote. In this case, it would be a quadratic asymptote. So you know that it's going up on both sides, but you also know how it's going up on both sides. Kind of neat. But you're not responsible for the equation of the quadratics. There's cubics, whatever you can imagine. Just the zeros, right? The horizontal asymptotes when the degrees are the same. And when the top is bigger by exactly 1, you have a slant asymptote. And how do you again find the equation of it? I forget already. Long division. Good. And it's going to be the quotient. Now, that's not to say that you are not responsible for finding the limit as x goes to infinity of something like this. But you're just going to find it by maybe saying positive, negative. They're both positive. You won't have to find the equation over the quadratic asymptote. Okay? Pretty neat, yes? I think it's pretty neat. All right, I'm going to stop recording there, and then we'll go on to the next one because we're caught up with the recordings. Bye, everyone. Say bye, everyone.